So that's not altogether clear the way it is introduced here, but we will see little bit later. So the way at this point I would say is you think of the Z rotation, and well, actually we have not found a geometric way of identifying what this A2 is in it. So for the time being, let this be, we'll come back to it. The whole molecule is considered and we consider all the axes in it and so on. Okay, so let's look at the second part. So the application of symmetry, and here as he says, he promises that we will learn something about IR and Raman spectra can be interpreted using symmetry. So here is a slightly more realistic molecule, and we are going to work out its character table and then also work out the spectroscopic content. So there are 2 nitrogens and 4 oxygens and 2 O4. This is a D2H. D2 basically meaning it is it basically, because the it doesn't have 90-degree rotation symmetry, only 180, but it has dihedral planes. So it has the plane which contains the molecule itself is part of the symmetry group. Now begins the physical thing where we will come to the rotations, the elements of rotation as well. So for N2 or 4, we may predict that there will be 3n minus 6 vibrational modes, because for any molecule, the 3 degrees of rotation which are just bulk translation of the molecule, and the 3 rotations which are just rigid rotation of the molecule as a whole, they don't enter spectroscopy. So they have to be subtracted out. So if there are 1, 2, 3, 4, 5 and 6 elements, then there are totally 18 elements, but out of which 6 have to be always subtracted. So 3 times the number of atoms in the molecule, 3n minus 6, that many vibrational modes can be there which stretch and strain the molecule. Now says we can find character tables to determine symmetry of all the 18 motions. This is where we will get into motions like Rx, Ry also, which are translations, rotations and vibrations. So first take each of these and assign x, y, z coordinate to them. Determine how each of the axes transforms for every class of symmetry operation in the group. Now because we are clever, we already know what are classes, we don't bother writing individual elements in a class. And this is the simple rule. If an atom moves, the character for all its axes is 0. If an atom is stationary and the axis direction is unchanged, then the character is +1. If atom is stationary, direction is reversed, then character is -1. And the sum of characters in each class, sum the characters in each class to determine the irrep of the whole representation gamma. So for each of the molecules we calculate these and then add to get gamma. So if we want the bulk representation gamma with identity containing 18 elements, as many as there are axes for each of the atoms, and then the characters are computed for each of the class of motions. So for example, you take C2, which is the 180-degree rotation around the z axis, and ask what happens under that to z. So following this rule, if an atom moves, then the character for all its axes is 0. So under z rotation, which is with this as the center of the molecule as the axis, if you rotate, all the atoms are rotating in it. So under this z axis rotation, the character is just 0. Then if you look under the same rotation, the fate of y, again all the atoms move, so you get 0. But the if you sorry, this was C2 of Z, so C2 of X, the oxygens all move, but the ends of the X are unchanged, and ends of the Y and Z are reversed. So in this case, X axis is this way. So after the rotation, the X of the two ends are not changed, but the Y and Z are reversed. So under a 180-degree rotation, this C2 is, so it is C2 fate of X. No, so sorry. So this is the C2 around the Z axis, this Z axis rotation, then the Y axis rotation. No, then Y axis, the atoms would not have moved. C2Y chi equal to 0, and ends of the X are unchanged. This is what happens if so it is not a Z axis rotation, sorry. So this is a C2 which is, so is computing this C2 which is about the X axis. The X axis is pointing this way, and if you rotate, then the X's are unchanged, but Y and Z are reversed, because you will carry out a rotation like this. So for individual atoms, its individual coordinate, you have to see its fate under this rotation. So under X rotation, this is what happens, and so the character of this C2X is -2, because that is the one in which at least two of the coordinates, the X components of these, are not touched. But the other two, everything moves. So around in the X axis rotation and in the Y axis rotation, everything moves. So you get zeros there. Then the reflection planes. So sigma xy, in the xy plane, only the Z axis is reversed for all the molecules, for all the atoms in the molecule. If you do a xy rotation, the Z axis is reversed, but X and Y axis are unchanged. So you get, for the reversals, you will get minus signs. For the things that remain unchanged, you will get plus signs. So totally you will get 6. I have not calculated this, but I think that is what it's saying, and so on. The YZ reflection, if you take the YZ plane and flip, all the atoms move, so character is 0. So there is a shortcut way of calculating the character of this given this is not an irrep. This you are doing the generic 3D rotations, and for that particular representation, one can just calculate all the characters, and under identity nothing moves, so we get 18 and so on. So so now the question is, how do we split this up into irreducible representations? And uses the theorem that we were quoting today, M alpha, the weightage of a particular irrep in a particular irreducible rep is equal to 1 over the size of the group times number of operations in a class, the pi, times the character gamma d times gamma star alpha. So character of reducible representation times character of the irreducible representation in that class, and sum over the class. This is our formula, right? You remember this formula. So now it begins to look very busy and complicated, but it is not really, except that he has filled out here the entire character table, which we don't have time to derive right now, and he has also borrowed, but you can let us see all the classes in it. So if you look at the top row, which lists all the classes, there is class of the identity, then there is class of C2Z, Z-axis rotation, Y-axis rotation, and X-axis rotation. So each one has different effects because there are two nitrogens lying along one axis. So if you do X-axis rotation versus Y-axis rotation, you get different classes. They are not equivalence class. And then there is full space inversion I, and then there are reflections in the XY plane which flip Z-axis, or XZ plane and ZX plane. Just if we look at the molecule once again, it's clear that all of these are possible. Okay. Yeah. So now this table is then filled out. This is the thing we are skipping right now, but in principle you identify this G, the Gerard, the ones that remain symmetric and the ones that are not Gerard, and so there are A's and B's. I don't know this notation or detail very well, but hopefully since we know there are these many classes, we expect that many irreps, and since there are that many ones available, we have to fill with ones or minus ones, and then by orthogonality, some we can guess and the others we can fill up by orthogonality. And we can also classify the properties, at least of XY I can argue, the RZ, RY, at least in this particular table. So at least in this table we can see that that RZ corresponds to, has the same properties as XY. So it is essentially XY rotation, and RY is XZ rotation, and RX is YZ rotation. So the product of the two axes has same property as the proper rotation in that plane. Okay, and these classes are, the irreps are identified by what they do to each of these, and then there are the ones that reverse the signs of X, Y, and Z. The point is we can construct this kind of a table for this molecule, and once you do it, you can now resolve your generic representation which you take to be 18 dimensional, where all the X, Y, and Z for each of the atoms is used as a carrier space. The carrier space now, which is not written here, the carrier space now is all the coordinates of all the atoms. For that representation, the identity will contain 18, it will be size 18 representation. So character of identity will be 18. And then these characters were figured out like on the previous page. So here is the resolution of this particular representation that was done on the, we can change from here, 4, So this particular character table that was worked out, it can be resolved into the irreps by using this, and one can find out the weightage factors of each of these. So that is filled up in the next page. So this is the statement now. The 18 sized reducible representation can be split up into the 1, 2, 3, 4, 5, 6, 7, and 8 classes. You can count here 1, 2, 3, 4, 5, 6, 7, and 8. So there is a mistake here. 8, not 18. 8 irreducible representations. This gamma can be split like this with the weightage factors as worked out here by doing the full orthogonality thing. So what does all this mean? Well, what now we can do is identify the properties of the vibrational modes. So now he points out that in this table, after all, there are, out of the 18 dimensional representation, 3 things are just the bulk motion of the whole molecule. So where X, Y, and Z axes move, and those correspond to B1U, B2U, and B3U. So they are identified here, B1, B2, B3. This is the fate of X, Y, and Z. And then there are rotations about the x-axis, y-axis and z-axis, and these happen to be B1g, B2g, B3g. So as you remember, U was G was symmetric, U was unsymmetric, and if you have two axes, then the signs of both cancel each other and remain symmetric. If you have only one axis, then you get a sign, so it remains unsymmetric. But these 6 are essentially to be removed once. Translations will contain each of these ones, and rotations of the bulk molecule will contain each of the B1, B2, B3g ones. So we remove one out of these. Okay, so B1u is here, it has weightage 2 here, we knock one of them off and we are left with 1 B1u. So let us see, 3 Ag, because Ag is not to be removed, but B1u should be only 1, yeah, so 1 B1u. So this 2 B1u becomes 1 B1u. The B2u, from 3 B2u it will become 2 B2u, and the B3u becomes 2 B3u. So we remove the contributions to this character which comes just from bulk motion of the molecule. Therefore what remains are all the vibrational degrees of freedom, and its size should be 12 now, this representation. This is the formula for vibrations. Generic vibration, you will have all of these present. Okay, and in fact he is pointing out what in physics we call normal modes. If you actually set up the Lagrangian of this system with the symmetries correctly, then you will find that you can diagonalize the, so you will have, let us say, interaction between n and O, but so the coordinates of this and coordinates of this will be coupled, coordinates of this and this will be coupled. So you will have a term like half kx squared, the potential energy is half kx squared. So if the strength of this bond is some spring constant k, then you will have 1/2 k times position of this O minus position of this n, the difference squared in the potential energy. So if you write the potential energy, if you now find the equations of motion which are derivatives of this, you will get linear terms. But so equation of motion x dot dot will contain x minus y, minus kx minus y. So the right hand side will be a matrix, this mixes x and y and z and so on. But the theorem, if you will learn in classical mechanics, is that you can diagonalize this matrix so that you identify vibrational modes that are eigenmodes of this matrix of oscillations. And that's what he has essentially indicated here, just heuristically. You can guess what will be eigenmodes, where you will not, those, so simplest mode he has shown is where each of the bonds stretches symmetrically by exactly same amount on all sides. Okay. This is one mode. Another mode where the two O's come together or go away from each other. So instead of focusing on only one of them, if you look at the collective thing, then it's easier to see what will be the eigenmodes. But algebraically you will find them if you carry out that classical mechanics canonical transformation of the coordinates. And so he has just tried to show physically what are reasonable eigenmodes. Okay, and then this direct stretch of only the NN bond, that is another one. So the point is that this motion will not mix with this motion, and this motion will not mix with, they are eigenmodes basically. AU mode is symmetric, so there is a rotation about this which will not mix with anything else. But now the main point is that, and this is the last part of this transparency, this set of slides, what is Raman active and what is IR active. Okay, so these vibrational modes, which ones will show up in infrared and which ones will show up in Raman spectroscopy. The character table tells us whether the vibrational modes are IR active or Raman active. For IR active, the vibration must change the dipole moment of the molecule. So the irreducible representations with x, y and z symmetry do this because the dipole moment is proportional to coordinate x, q times x. And so only the ones that, so from this list we retain only the ones that touch x, y and z, here bottom, as was shown on the previous transparency. This red box is the XYZ box, and that is the only one that really matters to IR. So drop the AG, drop the BG, drop all the G's and drop the AU as well, and you are left with 1 BU, 2 times 2 BU and 2 times 3 BU. And so these are the only things you will get in the IR spectrum of the molecule. And similarly, to be Raman active, I hope you all know what is Raman effect. It produces supplementary lines around the main line, and that happens due to polarizability. So to be Raman active, the vibration must change the polarizability of molecule, and this happens when the irreducible representations transform like the binary products of x, y and z. So either x, y is any of these, and that in this table is this set of actions shown here, and so only the G's matter, the subscript G elements matter. And you can now imagine why they have devised this notation, because the type G will all enter the Raman spectrum. So this 3, 2 and only the first 3 terms matter and the rest don't matter to it. And in fact the AU does not enter anything. We can check what is AU. So AU is this particular irrep where the 3 kinds of rotations did nothing, have character 1. I will not hazard a guess right now, but anyway, so we certainly note that AU has no specific properties under either X or under products of X and Y, and it does not show up in the IR or Raman spectroscopy. So that is basically the summary of this, and there is an example that has been worked out using this, which you can read because I have put up the transparency. This particular, just to explain what it is about, he says, how will you distinguish the same chemical content molecule, Ml3CO3 and so FAC and MER, where the chlorine and the O2 CO radicals are exchanged. Okay, so this chlorine and this CO basically are exchanged, but the rest of the stuff doesn't change its location with respect to some central thing M. And so he points out that this then, because of the symmetric placement of the chlorines, has a C3V symmetry, whereas this has only C2V symmetry, because now there is no rotational symmetry, only a 180 rotation. So therefore the weightages of the various symmetry classes will reduce between the two, and from that you can see that the FAC isomer is expected to have 2 peaks in both its IR and Raman, whereas the other one, which is only C2V, has 3 peaks and in both its IR. So this you can read out of this slide, but this is the practical way that this can be applied, and I will try to find out example that we can do reasonably within the portion we have covered.